Imagine you're an engineer with a 10,000 by 10,000 matrix. You need to solve it for 500 different low cases. You could run Gaussian elimination 500 separate times, or you could dramatically cut the total work. The brute force approach costs 500 times 1/3 n³ operations, but the smart approach using LU factorization costs only 1/3 n³ plus 500 times n². For n equals 10,000, that ratio works out to roughly 435 times savings. The secret is understanding where the cost hides inside elimination. So let's count operation by operation and discover where 1/3 n³ comes from. First, let's define our unit of work. A flop, short for floating point operation, is 1 multiply paired with 1 subtract. That's our basic building block for counting computational effort. Now picture an n by n matrix with generic entries aij. At the very first pivot step, we use the top row to eliminate every entry below the pivot in column 1. The pivot element is a11 sitting in the top left corner. For each of the n-1 rows below the pivot row, we perform roughly n multiply subtract pairs across the columns. That gives us approximately n-1 times n operations, which is close to n² flops. After completing this elimination step, the first row and first column are done, and they won't change again. The remaining active region that still needs work is an n-1 by n-1 submatrix. The second pivot step works only on the smaller submatrix, costing roughly n-1² operations. The third step costs approximately n-2². Each step shrinks the active region by 1 row and 1 column. This staircase of shrinking work continues all the way down to a single 1-by-1 block. So the total cost is approximately n² plus n-1² plus n-2², continuing all the way down to 1². The key question now is, how big is this sum of squares? The sum of 1² plus 2² all the way up to n² equals n times n plus 1 times 2n plus 1, all divided by 6. For large n, this is approximately 1/3 n³. Here's the intuition. Plot each k² as a bar on a chart. Now overlay the smooth curve y equals x². The area under that curve from 0 to n is the integral of x² dx, which equals x³ over 3, giving us 1/3 n³. As n grows, the discrete sum and the continuous integral converge toward each other. Let's check this with n equals 100. The exact sum is 100 times 101 times 201 divided by 6, which gives us 338,350. The approximation, 1/3 times 100 cubed equals 333,333. The error between these two values is under 2%. Therefore, we can conclude that Gaussian elimination costs approximately 1/3 n³ floating point operations. The matrix factorization costs 1/3 n³. Now let's count the cost for each right-hand side. With L and U already stored, solving AX equals B becomes just 2 triangular solves. Forward substitution solves LC equals B, working from top to bottom. The kth row requires k-1 operations. Summing 0 plus 1 plus 2 all the way up to n-1 gives n times n-1 over 2, which is approximately 1/2 n². Back substitution solves UX equals C, working from bottom to top. By the same logic, this is another 1/2 n² operations. Combining both, the total cost per right-hand side is 1/2 n² plus 1/2 n², which equals n². Let's put this in perspective. For n equals 1,000, that's 1,000,000 operations per right-hand side. The factorization, on the other hand, costs about 333 million operations. So each triangular solve is roughly 333 times cheaper than the original factorization. This is why we factor once and solve many times. Now let's see the payoff. Take n equals 1,000 with 100 right-hand sides to solve. First, the naive approach. Run full Gaussian elimination separately for each right-hand side. That's 100 times 1/3 n cubed. 1/3 times 1000 cubed is 1/3 times 10 to the 9th, which is about 333 million. Multiply by 100, and you get 33.3 billion total operations. Now, the smart approach using LU factorization, factor A into LU just once, paying about 333 million operations. Then for each right-hand side, do forward and back substitution at a cost of n², which is 1 million operations each. 100 right-hand sides cost 100 million more. The grand total is 333 million plus 100 million, which equals 433 million operations. Now look at the comparison, 33.3 billion versus just 433 million. And the LU approach is about 77 times faster. You get the same answers with 77 times less work. This is the practical motivation for LU factorization. By storing the multipliers in L and the reduced rows in U, we preserve the expensive 1/3 n cubed computation. It never needs repeating. Every new right-hand side costs only n². We show A equals L times U, where L is lower triangular and U is upper triangular. A large bracket encompasses the factorization, indicating this 1/3 n cubed cost is done only once. Below, we see multiple right-hand side vectors, B1, B2, B3, all the way to Bm. Each one passes through a forward and back substitution step, costing only n² each, producing solutions x1, x2, x3 through xm. The key takeaway, factor once, solve many times. 3 key takeaways. First, elimination costs approximately 1/3 n cubed. This comes from summing squares across shrinking submatrices, which leads to an integral that evaluates to 1/3 n cubed. Second, each right-hand side costs only about n², just 2 quick triangular solves, one forward and one backward. Third, LU factorization pays the 1/3 n cubed cost just once, and then what handles every new right-hand side for only n². This is exactly why every numerical library factorizes first and solves second. The lesson is clear. Find where the cost lives and do the expensive part only once.